Kim McKellar. When I was your age, I played a character named Winnie Cooper on a television show called The Wonder Years. You may be wondering what an actor like me knows about math and science. Well, in fact, I love science so much that I majored in mathematics at UCLA. On today's episode of NASA Connect, you will discover how ratios, proportions, and mathematics are found in nature, in our bodies, and in things we create. We'll also see how, in the near future, you may be taking driver's ed and flyer's ed at the same time. So prepare for takeoff as hosts Van Hughes and Jennifer Pulley pilot you through this episode of NASA Connect.
Hey guys, welcome to NASA Connect, the show that connects you to the world of math, science, technology, and NASA. He's Van Hughes.
And she's Jennifer Pulley. We're your hosts, along with Norbert. He's going to help us take you through another awesome episode of NASA Connect.
Right, every time Norbert appears, have your cue cards and your brain ready to look for answers to the questions he gives you. And teachers, when Norbert appears with a remote, that's your cue to pause the video and think about the problems he gives you. Got it?
Oh yeah, I got it.
Today we're in Kitty Hawk, North Carolina. This is where the Wright Brothers took the very first controlled powered flight in 1903. And guess what?
What?
They used mathematics, like ratios.
What is a ratio?
Good question. A ratio is a pair of numbers that is used to make comparisons, and ratios are everywhere. Get this, before the Wright brothers flew planes, they were experts in one of the most revolutionary means of travel since the wheel, the bicycle.
So, in memory of the Wright brothers' pre-flight days, let's use this bike as an example of a ratio.
Good idea, Van. Let's say we want to compare the number of revolutions or complete circles that one tire makes to the distance that the bike travels. Pretend this wheel measured 76 centimeters or 30 inches. By measuring the distance that the wheel rolled after one revolution, you can set up a ratio. One revolution to 239 centimeters.
Right. When you find ratios, you're also using proportions. A proportion is a number sentence or equation that states that two ratios are equal. How could you use ratios and proportions to determine how far your bike would travel if the wheel made 5 revolutions?
Simple. Set up a proportion like this. 1 revolution to 239 centimeters equals 5 revolutions to x, which is the unknown distance. Now, by cross-multiplying, we can see that the wheel would roll 1,195 centimeters in 5 revolutions. Notice that the fraction ratios are equivalent. Hey, here's another problem for you to try. If your bike wheel makes 1 revolution and travels 239 centimeters, how many revolutions would your wheel make if you traveled 2,352.3 inches? Be sure to watch your units.
So now that you have a better understanding of ratios and proportions, let's get back to the Wright brothers.
How did mathematics and ratios help the Wright brothers test and design their glider?
Before Flyer 1, the Wright brothers worked on bicycles. As young men, Orville and Wilbur started a bicycle manufacturing and repair company in their hometown of Dayton, Ohio. The Wright brothers used the money they made to finance their interest in aviation. In the winter of 1901, Orville and Wilbur Wright used their knowledge of math to build a wind tunnel in order to study how to control an aircraft. It was then that they realized the importance of ratios.
Right. The Wright brothers used something called the aspect ratio. That is the ratio of the wing's length to the wing's width. By increasing the length of the wing and at the same time decreasing the width of the wing, the Wright brothers cut the drag they experienced in their wind tunnel by half. Immediately, they began designing a better working glider.
In 1903, after adding a rudder, an engine, and a propeller to their aircraft, the Wright brothers achieved the first self-propelled flight of an airplane and began the era of powered flight.
Describe the growth of transportation since the early 1900s. What is mathematical about its growth?
Hi, I'm Ardith Williams, pilot and air traffic controller with the Federal Aviation Administration. Back in 1903, there was only one aircraft. Not much need for us to have an air traffic control system. However, by 1960, there were over 78,000 commercial and general aviation aircraft. And in 10 years, by the year 2010, we believe there'll be almost 228,000. Air traffic is growing and growing. We anticipate by the year 2010, almost 1 billion people will be traveling by air. The year 2003 begins century number 2 of aviation. I hope in 10 years or so, you will be one of the visionaries that will ensure my safe and efficient flight by designing, building, maintaining, controlling, or flying the aircraft. The future of aviation is in your hands.
You know, Ardith is right. Mathematical concepts are everywhere, and they help us explain the world we live in using a system of numbers. For example, remember when Ardith used a bar graph to explain the growth in the number of airplanes since the Wright Brothers? Well, get this. We can also create a graph to show the growth of all types of transportation, from cars to planes to jets to future aircraft. Look closely at this graph. Can you see a pattern? Patterns like the growth of transportation are everywhere. You just have to look around. Speaking of patterns, a man by the name of Fibonacci discovered a very famous pattern of numbers a long time ago in Italy. This pattern of numbers is called the Fibonacci Sequence, and the ratio of certain numbers in the sequence is so special, it's called the golden ratio. Hey, how would you like to meet an expert on Fibonacci? He's also a poet.
Hi everybody, this is Bud Brown talking to you from the Math Emporium at Virginia Tech in Blacksburg, Virginia. The Emporium is a large room with over 500 computers where students can come day or night to learn about math. And speaking of learning, here's a little verse I've written about a man called Fibonacci. How many ancestors do we have? That number is easily found. For we all have 2 parents, 4 grands, and 8 greats. Just double the previous round. But the family tree of the honeybee is not like any other. The girls, good and bad, have a mom and a dad, but each boy has only a mother. It's true, each drone has a mom alone, but each female has parents too. In addition, you see, she has grandparents 3, 1 fewer than me or you. And sakes alive, great-grandparents 5. That's even true for the queen. And next, twice great, that number is 8. And of thrice greats, she has 13. Now she's asking us, don't make a fuss, to do this calculation. How many ancestors does she have in every generation? So hop to it, folks. Let's crack no jokes. Don't stop for meals or for slumber. Just work your mind. The answer you'll find is a Fibonacci number. And now, to help you learn more about Fibonacci numbers, here's Jennifer.
Before we begin the student activity, let's learn a little more about the golden ratio and Fibonacci.
Who?
Fibonacci was a 13th century Italian mathematician who was studying a rabbit problem. He wanted to know how many rabbits he would have at the end of the year if he started with only 1 pair of newborn rabbits. Fibonacci knew that newborns are able to breed after 1 month, then every month after, if the conditions were right. He found that the sequence 1, 1, 2, 3, 5, 8, 13, and so on, demonstrated the total number of rabbit pairs at the end of each month. So at the end of the first month, you have the original pair of newborn rabbits. At the end of the second month, you still have the original pair because it took a month for them to become old enough to breed. At the end of the third month, you will have 2 pairs of rabbits, the original pair and their newborn pair. At the end of the fourth month, you have the original pair, their first pair, born the third month, and their newborn pair, born the fourth month. Following this sequence, at the end of month 12, you'll have 144 pairs of rabbits. Fibonacci and others soon found this sequence occurring in many other things in nature. By counting the spirals of pine cones, pineapples, and sunflower seed heads, for example, you can find neighboring pairs of Fibonacci numbers. The way in which leaves are arranged on a stem also displays a Fibonacci relationship. So do the spirals found in seashells. Now, Fibonacci wasn't the only one who was fascinated with these numbers. The ratio obtained by successive terms in the sequence was thought by the ancient Egyptians and Greeks to be special. It was so pleasing that they used this special ratio to design their pyramids, their temples, and buildings. You know the Parthenon? That's a great example of what has come to be known as the golden ratio or golden proportion. Here's the Fibonacci sequence. Let's see if you can determine the operation used and find the next 4 terms. 1, 1, 2, 3, 5, 8, 13. If you guessed 21, 34, 55, and 89 are the next 4 terms, you're right. How did you get it? The ratio of certain pairs of numbers in the Fibonacci sequence is used to describe things in nature. 1 to 1, 1 to 2, 2 to 3, 3 to 5, 5 to 8, 8 to 13, 13 to 21. If you divide the denominator of each ratio by its numerator, the results look like this. The ratios begin to get close to the rounded number 1.62. What if you divide the small number in the pair by the large number? Well, you'll get 0.62 rounded. If something in nature can be described using the ratios in the Fibonacci sequence, well then it's said to be golden. For more Fibonacci fun, let's visit Fairview Elementary in Dayton, Ohio, and Roosevelt Middle School in Springfield, Ohio. These students are in the SEMA program.
Hi, we're from Fairview Mass Academy, Dayton, Ohio. We're SEMA students. Hi, we're from Roosevelt Middle School in Springfield, Ohio. We're SEMA students.
NASA Connect asked us to help you learn this lesson.
There are many ways to divide the class up to check for the Fibonacci ratio in the objects you've collected, but we've decided to have 3 groups. The first group will measure natural objects. First, count the number of sides of the unpeeled banana. Write this number on the worksheet. On the pineapple, count the number of squares in 2 adjacent spirals. Are the adjacent numbers in the Fibonacci sequence? Count the segments of the half grapefruit. Is the grapefruit golden? Examine the pine cone for the number of spirals that go to the right and compare that number to the number of spirals that go to the left. Look at the daisy. Compare the number of petals that grow in a clockwise direction to the number that grow in a counterclockwise direction. Is your daisy golden? Now check any other natural objects that you have brought to class. The second group uses body measurements that approximate the golden ratio. Write the ratio of finger segments in one finger to the number of fingers on one hand. Is your hand golden? Now measure each student's height and record the results on the worksheet. Measure each student from the top of their head to the top of the middle finger of the outstretched arm. Record the results. What is the ratio of the height to the measure of the length from the top of the head to the end of the outstretched arm? Does it approximate the golden ratio? Measure the height of each student and the navel to floor height of each. Write the result as a ratio of body height to navel to floor height. Is the result close to the golden ratio? Measure each student's arm length and fingertip to the elbow. Write the result as a ratio. Is it golden? Group 3 measures man-made objects. Verify the Fibonacci numbers by measuring the length and width of an index card. Try this with an ID card. Measure other objects in the classroom or brought to class. When all groups finish with their explorations, they could summarize their findings and report to the rest of the class.
Special thanks to our AIAA student mentors from the University of Cincinnati.
Great job, guys! After you've completed the activity on the golden ratio, you should analyze your observations and respond to the following. In 4 sentences, describe the activity you just completed. Was everything you examined golden? How do you determine if an object is golden? Do you think that there is another special ratio, like the golden ratio, that exists in nature? Why?
Teachers, check out our NASA Connect website.
How are NASA engineers using Fibonacci Sequence and the golden ratio to research, design, and develop airplanes?
When NASA engineers are designing airplanes, they want to be sure that all their airplanes handle the same way. It's kind of like driving a car or a truck. Whatever car or truck you drive should perform the same way. Anyway, let's say engineers have designed a new airplane with a larger wing than a previous design. They have to use ratios to scale or size parts like the ailerons to fit the new wing. Ailerons are the movable parts of airplane wings that control roll. If the ailerons are not the correct size for the new wing size, the plane might not fly the way it should. So you see, the golden ratio helps designers determine the geometric relationships needed to keep the plane flying the same.
Hey guys, meet Bruce Holmes. He's an aeronautical engineer at NASA Langley Research Center in Hampton, Virginia. So Bruce, let us know what you're working on here at NASA.
Well, as Ardith told you, our transportation demand in this country will soar beyond supply in the new century, the 21st century. And we have just got to figure out how to make more places available to more people in less time. And so we're working with smaller airports and smaller aircraft that fly ever faster and ever safer than before to meet this 21st century demand.
You're telling me smaller airplanes? You mean like smaller, like this smaller right here? How is that going to happen, Bruce?
Well, many people don't know that the ratio of the total number of airports in the country to the number that have hub and spoke airline service is about 10 to 1. And so we can go 10 times as many places and save time for people if we can figure out how to use these smaller airplanes in smaller airports. I mean, there are several ratios that aircraft designers use to sort of score themselves as the design of the airplane. Wing loading, for example, is where you take the whole weight of the airplane and divide by the wing area that you see out here. And that gives you a sense of the relationship between the weight of the vehicle to how much area is supporting it. Another ratio that's very useful is the total lift efficiency or lift capability of the wing divided by the weight of the airplane. And that tells you how efficient of a lifting device the airplane is, and it also tells you how long the runway needs to be because it tells you how slowly you can land the airplane. Very important ratio.
Okay, so I guess what you're saying is that smaller airplanes mean smaller runways.
Much smaller runways. You know, big runways at big airports can be 10,000 feet, 12,000 feet, 15,000 feet long. And yet you can use a runway that's only about 2,000 feet, about 1/5 the length.
Okay, Bruce, this plane already exists, obviously. I mean, you fly this thing around. How are you and how is NASA going to use an airplane like this to help travel in the future?
The Small Aircraft Transportation System, which is using smaller aircraft and smaller airports as a means by which we can move more people to more places.
And you're working on this right now at NASA.
What we want to do with SATs is make it possible for people to have another choice for intercity travel in the 21st century, a bypass around hub lock and a bypass around gridlock. If you want to be in those systems for other reasons, that's fine. We'd like to give people an alternative. We're proposing to make these smaller airports all across the country more accessible in virtually all weather conditions, with airplanes that are as easy to use as cars and cost about the same as a car trip for long trips.
And about as small as this?
Well, the airplanes will be a little bit bigger than this. I mean, you'll be surprised actually at how big they'll seem once you get in. They'll seem more like minivans and things like that. So I mean, if you think about one of the other ratios or proportions that's interesting is how much power you have in the airplane relative to the weight of the airplane. We call it power loading, or thrust to weight ratio. And the people at NASA's Glenn Research Center are working on how to get more efficiency and more thrust out of less weight in engines.
This is like our little map here of telling us how to go. Let's plan a trip.
Are we there yet?
Gosh.
Well, here's how we find out. When you navigate, you pull out the map and you just kind of look at your route of flight, figure out where you're starting from and where you want to go to. And this was kind of a big mess. I mean, you know, the more you got into it, kind of the more involved this whole thing became. Oh yeah, and then peek over here and make sure everything's still going.
All right.
And we're going to put that away. Now it's all right here in the computer.
Oh, it's all right here?
Absolutely. So we can navigate, we can see where we are, we can see where the weather is, We can see where the traffic is. And we can see where we wanted to go, and we can also have all of the frequencies and all the information that was on that map is stored in the computer.
You don't have to use the map.
Push a button and pull it up. That's the idea.
Wow, and you've put all these technologies into this airplane.
This is an airplane that has many of the SATS technologies. There are many more to come, but this is sort of the grandfather of SATS airplane. So, Jennifer, Van, what do you say we button up and fly on over to the Research Triangle Institute and look at the computerized simulator where we can put some of this highway in the sky theory into action?
I love computers. Let's do it.
That sounds great. And you know, speaking of computers, did you know that the Boeing 777 was the first airplane ever to be designed completely using a computer? Isn't that right, Bruce?
That's right.
Yeah, they used computer technology, and it gave engineers immediate feedback and eliminated the need for building expensive models. So while Bruce, Van, and I head over to the Research Triangle Institute, why don't you go see Dr. Shelley Canwright and design an airplane using your own computer?
Many of you have been a passenger on an airliner, and I'm sure at least all of you have seen one flying across the sky. Maybe you've wondered what goes into designing one. Well, this show's online activity gives you the opportunity to model your own future passenger plane. By choosing different wings, tails, engines, and fuselage layouts, you can put together a complete airplane and see if it will fly. All of this right on your computer screen. Aided by computer analysis, you'll have quick feedback on the effect of each decision you make. The program you'll use is called Airplane Design Workshop, and it will give you an example of how artificial intelligence may be used now and in the future to assist engineers in the modeling and design process. Let's go to Central Elementary School in Pleasant Grove, Utah, where Mr. Bill Schuler's students will guide you through this activity.
Hello, I'm Bill Schuler, the technology specialist for Central Elementary School, and we're doing some problem-based education using desktop Arrow's aircraft design program. The students are pretending they are design engineers for an aeronautical firm. They have a contract with an airline to design an airplane, and if they design the airplane properly, they will receive a contract for the purchase of these airplanes and construction. If not, they'll lose the contract and the company will go bankrupt. So it's a little less than the economics too.
NASA Connect asked us to show you the aircraft design workshop developed by Desktop Aeronautics Incorporated. The main challenge with this activity is to see how fast you can fly and still meet the design requirements. First, we go to the NASA Connect website and click on the Norbert's Lab button to link to the online activity. At the top of the screen, you'll see a line of pictures. Click on the picture of the wing on the left side. Here you choose the sweep, size, and aspect ratio of your wings. Okay, now choose the next button, which gives you size, area, and aspect ratio choices for your tail. The next button, over, lets you choose the type of jet, amount of thrust, and number and placement of engines for your airplane. Now select the seating arrangement. This button lets you select the speed, altitude, and amount of fuel for your plane. Now you'll pick a final destination. All trips will start at Washington, D.C. With all these choices made, it's time to have the computer program analyze your selection. Click on the last button to evaluate your airplane. You'll find out if you're ready to fly. If not, you can go back to make other choices. The software program will suggest how you might improve your design.
Thanks for watching NASA Connect from Central Elementary. Bye!
We hope you will try your hand with this online activity. The program offers a rich foundation for problem-solving, reflection, and analysis. See what design situations you might create, and then use the software to solve them.
Hey, Bruce, you know, that looks a little familiar. It looks like Langley.
Well, it should. You know, the Fibonacci ratio we're learning about is also used by simulation engineers to recreate a very natural, lifelike appearance for grass, trees, buildings, skies, clouds.
That's really cool.
That is neat.
This looks like a big video game. What is the purpose of this?
Well, this is a simulator. Imagine, though, what it would be like if flying an airplane were a lot like playing a video game.
I'd be flying all the time.
You bet. Well, that's what we want to see happen. And so what we do is we try out all of the different kinds of images that give you a highway in the sky to follow. I think Jennifer, you, and Van should give this a try.
Oh, you got some confidence in this, Bruce.
You bet.
All right, let's try it out. Keep going.
There you go. Now, when you get up to about 80 miles an hour, you're going to gently pull back.
This is so weird.
Okay, now pull back. And you just left the ground.
Oh, and there's my pathway in the sky.
And there's your highway in the sky. Now you can steer with the wheel.
Okay, with the wheel.
You bet.
Oh, Bruce, this is so neat.
Yeah, and this is, the bottom of it is like the floor of the highway, and the top of it is the roof of the highway. Now it's like driving through a tunnel, if you will. There are no sides to this tunnel. And that tells you where you need to go. And it keeps you clear of everything that would be hazardous to you. Traffic, bad weather, obstacles, mountains.
Now, who else is on this pathway with me?
No one. This is your own pathway. Your computer created this for you because you told the computer before you got in where you wanted to go.
Oh, Bruce, this is so easy. I mean, this is great. I'll be able to fly like this right on to Richmond, won't I?
Well, we hope anybody can do this with a little bit of practice on a simulator to be safe.
You said anybody. I mean, you mean anybody, like, even like a van? Anybody?
I just got my driver's license. I could do this.
Right. You want to take the wheel? Left. Van.
Sorry, I got it.
Okay. All right. Well, while Van tries to take off, we'd like to thank everyone who helped make this episode of NASA Connect possible. Van, keep your eyes on the road. I mean, on the highway in the sky. You know, Van and I would love to hear from you with your comments, your questions, and your suggestions. So write us at NASA Connect, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681, or email us at connect@edu.larc.nasa.gov. Hey teachers, if you would like a videotape copy of this NASA Connect show and the Educator's Guide lesson plans, contact your local NASA Educator Resource Center, or CORE, the NASA Central Operation of Resources for Educators. All this information and more is located on the NASA Connect website. Good job, Van. Keeping it pretty level. All right. Okay, well, for the NASA Connect series, I'm Jennifer Pulley.
And I'm Van Hughes.
Van, hands on the wheel, please.
Oh, sorry.
Eyes on the highway in the sky. And we're closing in on Richmond, trying to get there. Will we ever get there? Good question. A ratio is a good question.
This is where the Wright brothers flew the very took.
Again.
What is a ratio?
Sorry, my fault.
No problem.
Got it.
Okay, here we go again.
Got it. This is.
Mathematics and ratios. That's okay. That's all right. Don't worry about it. No biggie.
So, Jennifer, Van, what do you say we button up?
Controlled powered flight in 1903. And guess what? They used mathematics like ratios. Partner?
We're SEMA students. NASA Connect asked us to show you how to do this lesson.
A ratio is a pair of numbers that is used to make comparison. While we fly on over to the Research Institute. Research.
Right.
Research.
Thank you for watching NASA Connect. Be sure to check out my website at danicamckellar.com, where I'll answer all your math questions and many more.